Hello, Math 122. In this video, we'll be talking about section 5.2, where we introduce the definite integral. So I'll start off with a bit of a review from last time. So remember from the last section that we developed this important fact, which I have outlined in the green box here. If we have a function f of t, and that function gives us the rate of change of some quantity with respect to time, then the total change in the quantity over an interval from a to b is equal to the area under the curve of f of t from t equals a to t equals b. And we represented this fact with a bunch of pictures, so I'll draw some of those pictures again. In this first picture, we have the function f of t as a blue curve in the plane, and then we have our endpoints t equals a and t equals b for our interval. And the area under the curve is given in purple here, and as long as f of t is a function giving us the rate of change of some quantity, then the total change in that quantity is equal to this purple area under the curve. So in the last video, we learned how to approximate the area under this curve by using rectangles. So we brought up the idea of a left-hand sum and a right-hand sum. In both of the pictures I have here, we're using a left-hand sum. But we can approximate this area under the curve by drawing rectangles that have height f of t sub I, where t sub I is the endpoint of each of these subintervals that we're using to break up the interval from t equals a to t equals b. So in this first example, we're using 5 different rectangles to approximate this area. And the approximation is pretty good when we're using 5 different rectangles. But if we want to get a better approximation, we can increase the number of rectangles that we're using. So in this case, it looks like we're using 8 rectangles. And you can see that the difference between the actual area under the curve and the area that's summed up with all of the rectangles is much closer in the second case than it is in the first case. And we eventually brought up the idea of using an infinite number of rectangles. So if I use as many rectangles as I want, can I get the exact number under the curve, or the exact area under the curve? And the answer is yes, and we'll be talking about that today. So remember that when we were taking the sum of the area of these different rectangles, we would get sums of the form looking like this, this sum that I have in green here. So we have f of t naught times delta t, where delta t is the width of each of the rectangles, or the width of the subintervals that I'm breaking up the interval from t equals a to t equals b with. And f of t sub I is going to be the height of each of the rectangles that are showing up. So this one here, this sum that I have, is a left-hand sum because we're summing up to t sub n minus 1 as opposed to t sub n. But we'll talk about a better way to write down this sum, a notation that's a little bit better. And again, the big idea from last time is that if we approximate with infinitely many rectangles, we can get the exact area under the curve, and today we're going to make that idea a bit more formal. Alright, so before defining the definite integral, I first want to bring up sigma notation, which is a new notation. Some of you may have seen it before, but it will allow us to take our left-hand sums and our right-hand sums and write them in a way that's not as tedious. This sum that I have written up here with all the different terms is kind of long, it's difficult to write out. But we can shorten that process a little bit by introducing a new notation. Okay, so we're going to let f of t just be some function, and to approximate the area under the curve of f of t over the interval from a to b using n different rectangles, we do the following. So this is something that was already in the last video, but just to remind you, we take this interval from a to b and we break it up into n subintervals because we want to use n rectangles. And if you think about it for a second, this means that the length or the width of each of these subintervals is going to be delta t equals b minus a, the length of the whole interval, divided by n, the number of rectangles we want to use. After doing that, we're going to take the endpoints of each of the subintervals and label them t sub I. So t naught, t sub 1, up through t sub n. And the left-hand sum is then going to be f of t naught times delta t plus f of t1 times delta t, and we keep adding these terms up until we get to f of t sub n minus 1 times delta t. And the right-hand sum can be defined similarly, just with a little bit of a change, but for now let's just think about the left-hand sum. So we can take this left-hand sum and we can write it using sigma notation. So let me just tell you how we would do that. we would write this kind of capital E looking thing, and we would say the sum from I equals 0 to n minus 1 of f of t sub I times delta t. So I'll say that again. The sum from I equals 0, the thing that's showing up on the bottom of the E, to n minus 1 of f of t sub I times delta t. So this is just a new notation that means this sum that's showing up on the right-hand side. So let me see if I can kind of explain what this notation means, where it's coming from. So this sum from I equals 0 to n minus 1 of f of t sub I times delta t is telling us to sum terms of the form f of t sub I times delta t, so all the stuff that's showing up inside of the sigma, for all integers from 0 to n minus 1. So these limits that are showing up on the top and the bottom of the sigma, those are telling us how many terms we're going to sum up. So we're going from I equals 0 to n minus 1, and all of the terms are going to have this form f of t sub I times delta t. So maybe I'll just write down a few of the terms. The 0th term, when I equals 0, is going to give me f of t sub 0 times delta t. The first term is going to give me f of t sub 1 times delta t. And the sum, or the sigma notation, is telling me to keep doing this process until I get up to I equals n minus 1. So I have f of t sub n minus 1 times delta t. And you'll notice this is exactly the left-hand sum that's showing up on the right-hand side of the equation above. Okay, a definition to keep in mind. So these sums of the form from I equals 0 to n minus 1 of f of t sub I times delta t, we're going to call these things Riemann sums. So we've also called them left-hand sums, we've called them right-hand sums before. In either case, a left-hand sum or a right-hand sum, we're going to call them Riemann sums. And we can approximate the area under these curves f of t using Riemann sums. And as we've already mentioned, we get better and better estimates as the value of n, or the number of rectangles that we're using, goes off to infinity. So as n gets bigger, we get better estimates. Okay, and as n gets really large, these Riemann sums that we've now defined, they're going to approach a single number. So the more and more rectangles we use, these Riemann sums are going to close in on a specific number, and that specific number is going to be the exact area under the curve. So we're not going to prove in this class that these Riemann sums will actually converge or approach this particular number, but at least in nice cases they are going to, and in all the cases we're going to look at. So now that we have sigma notation and Riemann sums under our belt, we can finally define the definite integral, which is going to be one of the main objects of study for the rest of the class. So we define the definite integral of a function f of t over an interval from a to b, so from t equals a to t equals b, and we write it with this fancy new notation that you probably haven't seen before. So we have kind of this uppercase S, and we say the integral from a to b of f of t dt. That's how I would say that. And we define it to be the value that these Riemann sums approach as the number of rectangles n goes to infinity. So we define these Riemann sums up above. We said as n gets really big, these Riemann sums are going to approach a specific number, and that number is going to be this definite integral. The definite integral is going to give us the same thing. Okay, so if we have a definite integral that's given to us, so the integral from a to b of f of t dt, then the function inside of the integral, f of t, is called the integrand of the function. So that's just some terminology for you. And the values a and b that are showing up at the top and the bottom of that integral, those are called the limits of integration. So here's an important fact about the definite integral. When the function inside of the integral, or the integrand, is greater than 0 all the time, so that function is always positive over the interval from a to b, then the definite integral, so this integral from a to b of f of t dt, is going to give us the exact area under the curve f of t from t equals a to t equals b. So it is defined to be that exact area under the curve f of t from t equals a to t equals b, as long as the function is positive. When the function is non-positive, so it's negative at some places, we'll talk about a bit of a difference in the next section. Okay, so here's our first example. With time t being seconds, the velocity of a bicycle in feet per second is given by v of t equals 5 times t, and the question is, how far does the bicycle travel from t equals 0 to t equals 3? Okay, so to figure this out, we are going to draw the function first. So first off, notice that the velocity function, 5t, is linear, and more than just that, it passes through the origin. So if I graph it, I will get a graph that looks something like this. So we have a line. We'll say this is time equals 3, and up here, this is going to be velocity 15 feet per second. So this is just a good enough sketch for us to do the problem. All right, and we know from last section that the total distance traveled is given by the area under this line from t equals 0 to t equals 3. So let me just kind of sketch out what that area is that we're looking at. This area in red is going to give us the total distance that the bicyclist has traveled. Okay, so we can write this area using integral notation. So we have that the total distance traveled is equal to the integral from 0 to 3. So we start at time equals 0, we go to time equals 3, of the velocity function dt. So this definite integral is going to give us the area under this curve that I have sketched above. And in our case, the velocity function is 5 times t, so we'll replace v of t with that. So 0 to 3 of 5t dt. So this is how we would represent the area under that blue curve using integral notation. This also means the total distance that the bicycle has traveled from t equals 0 to t equals 3. They're the same thing. Okay, so this integral literally means area under the blue curve, but in this case, because our blue curve is a line, the area under the curve is just the area of a triangle. So we can use some geometry to figure out what this definite integral is going to be. So the area of a triangle is 1/2 times the base of the triangle times the height of the triangle. And in this case, the base of the triangle, since we're looking at the interval from 0 to 3, the base of the triangle is going to have length 3. And the height of the triangle, we're going up to 15 feet per second. So we're going to have a 15 for the height of the triangle. And this will give us a 22.5 feet. So in this very special circumstance, we can actually calculate the definite integral just by using some rules for area that we have from geometry, but that will generally not be the case. So we'll think about that more in the next sections. So although we got lucky in the previous example, and we happen to be able to use geometry to calculate the definite integral, usually we're going to have to revert to our calculators to solve these definite integrals. But fortunately, graphing calculators and a lot of computer algebra systems have the ability to calculate these definite integrals for us. So in this section, I'll describe how you can do that. So for an example, let's say we want to compute this definite integral from 0 to 1 of the function e to the negative t squared dt. And we can compute it using a computer or a graphing calculator. And in this case, there's actually really not a nice human way to compute this integral. We're going to have to use a computer to approximate for us. So I gave two different solutions here. The first one, we're going to use Desmos, and this one I can actually go over on my computer and show you what to do. Okay, so over in Desmos.com, we can type in int, and this will give us the integral symbol, and now we're integrating from 0 up to 1, and we're integrating the function e to the negative t squared, and now we're just going to put a dt so that Desmos knows we're integrating with respect to t, and we get this answer of 0.746 and so on. So you can tell that in this case it would not be nice to calculate whatever this number is by hand, so it's nice that the computer will do it for us. And while we're here, let's just look at what this function e to the negative t squared looks like as a graph. So we get this, this function over here in purple, and this definite integral is supposed to be representing the area of this function, or under the curve of this function, from t equals 0 over to t equals 1. So if you want to, you can pause the video and just kind of convince yourself that the value we got for the definite integral does in fact give us this area. Okay, so for Desmos, doing this calculation really isn't too bad, and the same thing happens for the calculator. The calculator is also set up really nicely, but calculators can be a little bit different from calculator to calculator, so you might need to just look up how to do it on your specific calculator. Just go on the internet, it should be pretty easy to find. So a couple of different things can happen when you look for that integrate function on your calculator. You might have this int with a parenthesis show up, something like that. If that's you, then to do this integration, you want to first enter the integrand, so the function that we're looking at, and then comma, and then the variable that you want your calculator to integrate with respect to. And then in the last two spots, you're going to put the limits of integration. So in this case, you'd put a 0 and a 1. If you have a TI-84, I think that you're going to end up with this kind of notation that will appear, just like it was in Desmos. And in this case, it's pretty easy. The interface is pretty nice, and you can just plug in the relevant limits of integration and the appropriate integrand, and everything should work out fine. But in both cases, in Desmos and in the calculator, you should get this answer of 0.747. And again, that answer is giving us the area under the curve e to the negative t squared from t equals 0 to t equals 1. Okay, and finally, just a few last examples for you. So remember that we were able to approximate the area under the curve using left-hand sums or right-hand sums. And since we define this definite integral to have that interpretation as the area under a curve, and we'll make this more explicit in the next section, we can also use left-hand sums or right-hand sums to approximate a definite integral that's given to you in the first place. Okay, so in this case, we're given this definite integral from 20 to 30 of the function f of t, and I don't know what that function f of t is, but I'm given a table that gives me a bunch of different data about the function f of t, and it looks like in this case I have 5 different intervals that I'm working over here, from t equals 20 to t equals 30, and we can use left and right hand sums to approximate this definite integral. It won't be perfect, but it'll be pretty good. All right, so I would say that this integral, maybe I'll go to a different color, this integral from 20 to 30 of the function f of t dt is approximately, and now I'm going to set up the left-hand sum. Okay, so I'm going to look at f of 20 times delta t, the width of each of these subintervals, which is going to be 2 in every case, plus f of 22 times 2, plus f of 24 times 2, plus f of 26 times 2, plus f of 28 times 2. So this is my left-hand sum, where I'm using 5 different smaller subintervals from t equals 20 to t equals 30, and this is going to approximate the definite integral. I can make this look a little bit better. So I get a 5 times 2, plus a 7 times 2, plus an 11 times 2, plus 18 times 2, plus a 29 times 2. And if you add all of this together using your calculator, you end up with 140. So if we do a left-hand sum with 5 different subintervals we get that the definite integral is approximately, and it's important to note this is just an approximation, it's approximately 140. We can also use a right-hand sum. So in this case, we have that the integral from 20 to 30 of f of t dt is approximately f of 22 times 2, because now we're using a right-hand sum, plus f of 24 times 2, plus f of 26 times 2, plus f of 28 times 2, plus f of 30 times 2. And again, we can plug in the actual values for each of these values of the function. So we get 7 times 2, plus 11 times 2, plus 18 times 2, plus 29 times 2, plus 45 times 2. And again, if you take this sum and you put it into a calculator, you should end up with 220. So when we do the right-hand sum with 5 subintervals, we get an approximation for the definite integral that is 220. Okay, so both of these sums approximate the definite integral 20 to 30 of f of t dt, and we can get a better estimate of the actual definite integral by averaging the two values that we got for the left-hand sum and the right-hand sum. So then we would say that the definite integral from 20 to 30 of f of t dt is approximately 220 plus 140 divided by 2, which would give us a 180. So this 180 would be a bit of a better approximation of what the actual definite integral is. All right, and in this last example, instead of being given a table, we're given what the function or the integrand inside of the definite integral actually is, but we're still going to approximate using a left-hand sum and a right-hand sum. So for part A, let's approximate the integral from 0 to 6 of 4x minus 3 dx using a left-hand sum with n equals 3. So we're breaking up the interval, maybe I'll write, break the interval from 0 to 6 into n equals 3 subintervals. So we're looking at the values t equals 0, t equals 2, t equals 4, and t equals 6, because this allows us to break up the interval from 0 to 6 into 3 parts. We have the interval from 0 to 2, from 2 to 4, and from 4 to 6, and now we can calculate a left-hand sum. So the left-hand sum is going to equal f of 0 times 2 plus f of 2 times 2 plus f of 4 times 2. And maybe I should say here that this f that I'm using, f of x, is equal to 4x minus 3, my integrand. And now I can evaluate what f of 0, f of 2, and f of 4 actually are. So we get 4 times 0 minus 3 times 2 plus 4 times 2 minus 3 times 2 plus 4 times 4 minus 3 times 2. I can simplify. I get a minus 3 times 2 plus a 5 times 2 plus a 13 times 2, and this will give me a minus 6 plus 10 plus 26, and I should end up with a 30. So in this case, this definite integral from 0 to 6 of 4x minus 3 dx is approximately 30, using this left-hand sum with 3 different subintervals. Okay, we can approximate it in a different way too. This time let's do a right-hand sum with n equals 2. So we'll break this interval from 0 to 6 into n equals 2 subintervals. So this time we're looking at t equals 0, t equals 3, and t equals 6, because this will break up that big interval into just 2 subintervals of equal length, 3 in this case. All right, and now we have the right-hand sum is going to be f of 3 times 3 plus f of 6 times 3. So notice here, instead of multiplying by 2, we're multiplying by 3 because the length of each of these subintervals is now 3. And because we're using a right-hand sum, we're using f of 3 as opposed to f of 0, and f of 6 as opposed to f of 3, like we would in the case we were doing a left-hand sum. So let's plug this into our function. We get a 4 times 3 minus 3 times 3 plus a 4 times 6 minus 3 times 3, and now we can simplify. We get a 9 times 3 plus a 21 times 3, which will be a 27 plus a 63, and this will give us a 90. So this approximation is much different than the previous one. This time, the approximation for the definite integral, we have a 90, using the right-hand sum with n equals 2. And just to see how close these approximations are, let's take this definite integral from 0 to 6 of 4x minus 3 dx, and just plug it into a calculator and let the calculator tell us what it is exactly. So I'm going to go over to Desmos. Okay, so we take our function and we're going to integrate. So we integrate from 0 to 6, and we're integrating the function 4x minus 3, and now we put a dx so that Desmos knows we're integrating with respect to x, and Desmos will just pop out 54 for us. So if I go back, I can say that the actual value of this definite integral is 54. And you can see that the actual value is pretty close to being in between the value that we got from the left-hand sum and the right-hand sum. But neither of those approximations was very good because the value for n was low in both cases. We'd have to increase the number of rectangles we were going to use if we wanted the approximation to be better. But in future videos, we will talk about methods that we can use to calculate these definite integrals for ourselves much more exactly than the approximations that we're doing. But this should be enough information for you guys to get through your homework, and I'll see you in section 5.3.